Okay, so I think we should get started. So today's speaker is Professor Shu Heng Shao, and he will tell us about the new types of symmetry. So we learned in undergraduate quantum mechanics that if you have symmetry in the system, those symmetry can be realized as unitary operators acting on the Hilbert space. We learned in the last 10 years or so that that's not necessarily true. And there are lots of very exciting applications of this idea, ranging from condensed matter physics to high energy physics, etc. And he will tell us about that. So Professor Shao received a PhD from Harvard and was a long-term member at the Institute for Advanced Study, and was a faculty member and still is, I think, at Stony Brook University, Institute for Theoretical Physics. But this summer he moved to MIT, where he is a faculty member. And okay, so please welcome Professor Shao. The title of his talk is "What's Done Cannot Be Undone." Okay, please.
Right. Thank you so much. All right, thanks for the very nice introduction. It's so nice that you actually stole all the contents on my first slide, but we'll get to that. So, well, it's great to be here to visit Caltech, to see a lot of old and new friends. I was hoping the weather would be better, but it's okay.
You brought one from Boston.
Yeah, blame it on me. I checked the temperature. It's actually colder here than Boston today. All right. So anyways, it's great to be here. So I'll talk about a new kind of symmetry today. And it's called non-invertible symmetry. And as Hirosi already said in his introduction, ordinary symmetries are invertible. In fact, by Wigner theorem, they have to be implemented by a unitary or anti-unitary operator in quantum mechanics. Now, one fun fact about unitary operator is that it has an inverse. Take your unitary operator U, take its dagger. That's its inverse. That's the definition of a unitary operator. Together, these unitary operators form a group. And indeed, every group element has an inverse element. That's the definition of the group. However, in recent years, there has been a lot of developments in a new kind of symmetry, known as the non-invertible symmetries. As the name suggests, they are implemented by conserved operators. These are operators commute with the Hamiltonian, and yet they don't have an inverse. Even though it sounds very exotic, they lead to new conservation laws, new selection rules, new constraints on renormalization group flow, and they have appeared in quantum field theory, particle physics, condensed matter physics, and many more contexts. At this point, you might think, okay, this sounds totally exotic. Maybe I have to work really, really hard to find the simplest non-trivial non-invertible symmetry in the quantum system. For me, as a string theory, maybe you would think you have to go to 11 space-time dimension with 32 supersymmetry to find the simplest such example. Which, by the way, if you do go to 11D with 32 supersymmetries, that's the low energy limit of supergravity, and that does have interesting non-invertible symmetry, but that will be another talk. For the simplest example, you don't have to look far. In fact, already in the 1 + 1D quantum Ising lattice model, there is one such non-invertible symmetry, and that will be what the first part of the talk will be about. So in the following 5 minutes, let me go through this model and talk about how to, what this new symmetry is about. So the setup is going to be a discrete space, which is a 1D spin chain. It has L sides. On every side, you have a qubit, which can point up or down, or any linear superposition thereon. I'm going to work on a circle with periodic boundary condition. So I'm going to identify this label J with J + L. Every qubit has a two-dimensional Hilbert space. I have L of them. So in total, I have a 2 to the L dimensional Hilbert space. Most of the things I'm going to say will hold true for finite L. So when I say operators in the coming 5 minutes, that's really just a fancy word for a 2 to the L by 2 to the L matrix. If you get so bored about my talk, you are welcome to take up your laptop and code every matrices I'm going to mention into Mathematica. It takes you 2 lines, and you can check every statement. So the space is discrete, which consists of this L site, but the time is continuous. So I'm going to specify a Hamiltonian that describe the time evolution. And the Hamiltonian I'm going to use is just the ordinary Ising lattice Hamiltonian. Here, X stands for the poly X matrix. Z stands for the poly Z matrix. And you have such a pair of matrices at every site. And this Xj is just a tensor product of X on the J side with identity elsewhere. This is a family of Hamiltonians labeled by a continuous parameter G. So why do we care about this Hamiltonian? In fact, this is the simplest possible leading Hamiltonian you can write down if you impose two ordinary invertible symmetries. In fact, I promise you, I'm not going to make these two invertible symmetries non-invertible down the road. They're really honest to God, ordinary symmetries. The first one is the defining symmetry of the Ising model. It's a spin flip symmetry. It takes all the spin from up to down and vice versa. In this presentation, the spin flip symmetry is taken to be the product of all the poly X, denoted by V. We flip the sign of every poly Z operator, but keep the poly X invariant. As I say, flips all the spin from up to down and vice versa. Imposing this Z2, this is the simplest kind of Hamiltonian you can write down. You allow for a linear term in X, but you have to have quadratic term in Z. Furthermore, I'm going to impose lattice translation, which is take you from site J to site J plus 1. All right. Now, what's the phase diagram? The phase diagram, as a function of G, looks as follows. So you take the system size L to be larger and larger, and you are curious about the low energy state of this Hamiltonian. So let's go to the extreme limit. If you take G to be very, very small, then you can forget about the first term and focus on the second term. Then it's preferable to diagonalize your state with respect to the poly Z basis. To minimize the energy, all the spins can all be pointing up, or they can all be pointing down. They will have equal energy. In the thermodynamic limit, these two states will become degenerate, and the Z2 spin flip symmetry will take you from one such ground state to the other one. This represents an ordinary spontaneous symmetry breaking phase of a Z2 global symmetry. In condensed matter physics, this is known as the order phase because the superselection sectors have all the spins pointing in one direction. If you are field theorist, you can think about it as a double well potential, where the Z2 symmetry is spontaneously broken. In the opposite limit, you take G to be plus infinity. In that case, you focus on the first term and forget about the second term. In that case, it's preferable to diagonalize your state with respect to the poly X basis. And you will have a unique ground state. And that state will respect the spin flip symmetry. So this is a symmetry preserving phase. In condensed matter physics, that's known as a disorder phase. The reason is because if you write this eigenstate of the poly X operator in terms of the spin up and spin down basis, it's a superposition of all possible spin configurations, and therefore it's a disorder. Since the phases at the opposite two ends of the parameters space are different, there has to be a phase transition somewhere in between. And this happens exactly at G equals 1, where it is a second order phase transition described by a gapless continuum quantum field theory. And that's arguably the simplest possible quantum field theory of all, is the Ising conformal field theory. Okay, so this is the simplest possible phase transition, and it fits into Landau's paradigm. Landau paradigm says that every phase has to be represented by how the symmetry is characterized. And you go from a symmetry preserving phase to a symmetry breaking phase, undergoing through a second order phase transition. So far, everything I said you can find on Wikipedia. I haven't said anything yet. The question we would like to ask in this talk is that let's say I set right at the G equals to 1 point, the critical point, for which the thermodynamic limit will be given by the Ising conformal field theory. Is there an additional symmetry, in addition to the spin flip and lattice translation symmetry of this lattice Hamiltonian? If you ask someone on the street this question, the answer you are probably going to get is, yeah, there's a Kramers-Wagner transformation that leaves the Hamiltonian invariant. So what is the Kramers-Wagner transformation? It maps the poly X to a product of Z's, maps a pair of Z to a single X. You look at your Hamiltonian, you apply this transformation, And you see that precisely when this coupling constant G is set to be 1, there's a symmetry exchanging the two terms. So that seems to be a symmetry. But if you ask yourself harder, why is that solved? Well, you have a Hamiltonian, and it's made out of some operator. You write down some transformation rules for the operator. That leaves the Hamiltonian invariant. What else can you ask for it to be a symmetry? This is how we learn symmetries in quantum field theory too. In quantum field theory, you have a Lagrangian. It's made out of some field, scalar field, phi. And there are some transformation rules on the phi, maybe flip phi to minus phi. And you find your Lagrangian invariant under the symmetry transformation. That by all means should be called a symmetry. In fact, if you look at the original paper by Kremers and Wigner back in 1941, they call it the symmetry property of the critical Ising model. Kremers and Wigner were pretty serious physicists. We should probably listen to them. However, if the person you ask on the street happened to be Wigner, then Wigner would have asked, well, you call this a symmetry. Is this symmetry implemented by a unitary operator, as my theorem would have predicted? The answer to this question, however, is no. There cannot possibly be a unitary operator that implements this Kremers-Wigner transformation. So bear with me in the following 1 minute. I'm going to prove this no by contradiction. It's probably the most complicated math we're going into in the entire talk, but it only takes 3 lines.
Can you define it as an action on the basis of states? You've just talked about what it does to the operator.
So yes, so here I define symmetry. So it's a question about what do we mean by a symmetry? And there are so many conditions we would like to impose on the symmetry. And I'm not giving you all the definition. So I start from a Hamiltonian lattice distance. And by symmetry, I feel at the very least, it should be conserved in time. So you should commute with the Hamiltonian. It will induce some action on the state, which I'm happy to talk about later on. But in this Hamiltonian formalism, let me stick to this very, very minimal condition I would like to impose on the symmetry. All right, so let's see why this is no. So we're going to prove by contradiction. So let's suppose there were such a unitary operator that implements this Kremers-Wigner transformation. I'm going to call this operator U. So by Wigner theorem, what he meant by the unitary operator implementing the symmetry transformation is that when you conjugate the operator by this U, it should give you the right-hand side of the transformation rule. The UX U inverse better give you Vj Zj plus 1. However, if you apply this transformation on the spin flip symmetry, which I call V, let me remind you, V is defined as a product of all the X on your periodic chain. This is the definition. Then you can bring this conjugation action to each individual poly X operator. And following this rule, X1 becomes Z1, Z2, X2 becomes Z2, Z3, XL becomes ZL, Z1. We are on a closed periodic chain where every single Zj will appear exactly twice. And therefore, they pairwise cancel. And this entire expression boils down to 1. Starting from this, you can multiply U inverse on the left and U on the right. And that will tell you V, the spin flip symmetry, is an identity operator. But that cannot possibly be the case. We just talked about the phase diagram of the Ising model. The O spin up state is a different state compared to the O spin down state. So this is a contradiction. So that finishes the proof why the Kremers-Wigner transformation cannot possibly be implemented by a unitary operator. And that gives you the first hint that there's something that goes beyond the paradigm set by Wigner theorem, even in the simplest possible many-body quantum system. And if there's any lesson to be learned from this simple reasoning, is that in physics, we should never write arrows. When you write arrows, you don't really know what you are talking about. Do we mean a unitary conjugation or do we mean something else? Now, we're serious people in physics. So we should really write equalities rather than arrows. So that begs the question, when we wrote this Kremers-Wigner transformation, what are the equalities behind it? What do we really mean? Is there a conserved quantity associated with this arrow? So I'm going to tell you the answer without giving you the derivation. In fact, I think there are maybe at least 5 or 6 different derivations of the answer I'm going to present to you in the next slide. I'll be happy to talk about the derivation afterwards. So here's the answer. The answer lies in this rather complicated operator, which I call D. So don't panic. It looks a little bit complicated, but I'm going to walk you through most of the important aspects of this operator. The first thing you have to notice is that it's a very explicit operator. I'm not hiding any details or using any obscure notation. Everything is made out of the poly X and poly Z. And calling it an operator is an overkill. For finite L, this is just a gigantic matrix. And everything I'm going to say holds true for finite. So let's go through this, the details of this operator. First, there's a gray piece. And the reason I put it in gray is because I don't want you to pay too much attention on this normalization factor. But there's actually something very deep about it. The root 2 is actually signaling a Majorana zero mode that's related to this operator D. The phase factor is also interesting. There's a factor of 8. And that factor of 8 is related to an anomaly that's commonly studied in superstring theory. And that 8 is related to the critical space-time dimension of string theory. But again, I'm not going to spend too much time on this gray factor, but there's actually something, an interesting story behind. Moving on, let's look at the blue piece. The only thing you need to know about the blue operator is that every individual factor in this product is a unitary operator. That you can check in real time. Take any one of these factors, multiply it by stagger, that's going to be 1. The product of unitary operators is going to be a unitary operator again. So the only thing you need to know about this blue operator is that it's a unitary operator, which I denote by U sub kW. In fact, this operator was recently discussed in this very nice paper by Shea Chen and Nat and collaborators in the context of a sequential quantum circuit. It's a quantum circuit where at every step, the gate only adds on 2 neighboring site. Finally, there's a red piece of the operator. That is a projection operator. What is a projection operator? A projection operator is something that gives you 1 on the symmetric sector and give you 0 otherwise. Indeed, when the spin flip operator takes eigenvalue plus 1, this thing gives you 1. On the other hand, on the negative eigenspace, this will give you 0. Projection operator, by definition, has a huge kernel. Whenever the state carries an odd Z2 charge, this is going to give you 0. And therefore, this entire operator D is going to be non-invertible. And what do I mean by that? It just means that this matrix has 0 eigenvalues, and therefore the inverse does not exist. Nonetheless, I claim this operator does the job. It implements the Kramers-Wigner transformation in the following sense. When you multiply D with xj, it equals zz times D. This equation looks awfully similar to the one we encountered in 2 slides ago. However, here I move the operator from the right-hand side to the left by taking the inverse. The only difference here is that I didn't dare to move the D from the right to the left. In fact, I couldn't because the D has a kernel, and it's a matrix that doesn't have an inverse. And that's how we evaded the contradiction we encountered in the previous slide. So this is a non-trivial operator. It's not a number. It acts non-trivially on the state, which I'll be happy to talk about more after the talk. And it obeys the following equations with x and zz. And because of that, at the critical point, it commutes with the Hamiltonian. And therefore, it leads to a conserved quantity that doesn't depend on time. And there are similar maps or operators that are also discussed in this related papers. Now, you might be a strong believer of Wigner theorem and say that, okay, you show me this complicated operator. Why can't I just work with the blue part? This UKW is pretty nice. It's unitary. Why doesn't it do the job? If you force yourself to commute UKW with the Hamiltonian, you'll realize that it doesn't exactly commute with the Hamiltonian. It makes a mistake at one site. What's good about it is that it's invertible. In fact, it's unitary. On the other hand, for this operator D, it is not non-invertible, but it is a true quantity that commutes with the Hamiltonian. So in this particular case, it seems like you cannot have both. You either have an operator that's invertible, but it's not conserved, or you have something that's conserved, but it's non-invertible. But I would like to advocate that this is really a feature of the system rather than a bug. All right, so I spent so much time talking about the Ising model. The Ising model is exactly solvable. We don't want to solve the Ising model for the 100th time. So what is this symmetry good for? Oh, actually, before that, I have something else to say. So for the Ising model at the critical point, we now have the lattice translation. We have the spin flip symmetry. We also have this new character in the game. Whenever you have a collection of symmetries, the first thing you should do is to put them together, to multiply them together. For ordinary symmetry, you are going to find the group. Here, what are we going to find? For this spin flip symmetry, if you square it, you get the identity operator. That's a Z2 group. There's nothing shocking there. What happens if you square this operator D? The moment you square it, you don't get a single operator on the right-hand side. On the other hand, you get a sum of two elements. The first one is a lattice translation. The second one is a spin flip symmetry multiplied by the lattice translation. This shows immediately that this is not a group. In groups, when you multiply A with B, you're just going to get one single group element C on the right-hand side. But here you get a sum of two things. And that gives you a hint that we're going beyond the paradigm of group theory. So what is this good for? What can we use this new symmetry for? For that, let me quickly say that what do people usually care in many-body quantum system? Well, there are many things one can talk about, but one thing in particular is that suppose someone hands you a Hamiltonian with many interacting degrees of freedom. You want to determine its phase diagram in the thermodynamic limit. You want to organize all these different many-body quantum systems by their universal features of the low energy phase. And here are three possible scenarios for the thermodynamic limit of a many-body quantum system. It could be that as you take L to infinity, you have a unique ground state, and the gap remains order 1, doesn't scale with the system size. This is like the most trivial possible scenario. In the low energy limit, all these excited states are pushed to infinity. You have a unique ground state, and it's completely featureless. Or you could have several degenerate ground states, and an order 1 gap above it. Or you could have a gapless spectrum where the spacing between the energy eigenstates goes to 0, maybe scale as 1 over L. To determine which one of the scenarios you actually realize in a given Hamiltonian is generally a non-trivial question. The interactions between the different qubits can be strong, and you typically need non-perturbative rules to give you constraints on the low energy phase diagram. So let's talk about one particular example. You can start with the critical Ising model and ask certain next to nearest neighbor interaction. This kind of deformation has been considered in many places, including this very nice paper. This particular deformation shown in blue preserves both the spin flip symmetry and the new non-invertible symmetry we just talked about. In this paper, they used DMRG to find the phase diagram for this model. I also include the parameter G, which will preserve the spin flip symmetry, but break the non-invertible symmetry. But let's focus on the horizontal line. Along this horizontal line, both symmetries are preserved. This is the origin of the model that we talk about. It's described by the Ising conformal field theory. When you turn on this deformation a little bit, it's not going to change the phase diagram. It stays the Ising gapless conformal field theory for a while. That means this deformation from the CFT point of view is an irrelevant deformation. In fact, for experts in the audience, that's known as the TT bar deformation. Then at some point, there's something interesting happens. It becomes a different CFT. It's known as the tricritical Ising CFT. The details don't really matter. And after which point you reach a phase that's gap with 3 degenerate ground states. Now, the only thing I want you to notice is that along this entire horizontal axis, the phase is never trivial. You are either in this scenario or in this scenario. You never have a scenario where the ground state is gap with a unique ground state. Is that an accident of this particular deformation, or is it something more generally true? So this is what was addressed in these papers, where it was shown that any Hamiltonian that commutes with the non-invertible symmetry D that I talked about earlier, in the thermodynamic limit is either gapless or gapped with three degenerate ground states. So it tells you that among the three scenarios, the first one is actually ruled out. It's a non-perturbative constraint that you can use to study your many-body quantum system. So in the Ising for the region that's described by Ising CFD, you realize this scenario. For the region that's gapped with three degenerate ground states, that's this case. You might be curious about where the three comes from. But in physics, we are very used to having a factor of 2 or minus sign. Where does the 3 come from? Now, there's actually something very easy, an easy way to understand it. When you turn on that G coupling constant, the original constant in the transverse field Ising model, for one sign, that will take you to the order phase where you have 2 ground states. For the other sign, that will take you to the disorder phase where you have a unique ground state. The existence of the non-invertible symmetry tells you that order and disorder have to coexist. So it's either a gapless second order phase transition, such as in the case of the green line, or it's a first order transition between the two. And the 3 comes from the level crossing between this pair of states and the disorder states up there. All right. So that's what I wanted to say about the lattice model. Now you might wonder, can such example also exist in field theory, in continuum quantum field theory? In fact, I think many of these studies come from the field theory analysis. I'm kind of telling the story backwards. And I'm going to focus on one particular example of non-invertible symmetries in field theory. And the theory I'm going to talk about is no other but the quantum electrodynamics for our real world. So this is QED in 3 + 1 dimensions, but in the limit where we take the electron mass to be 0. This is the quantum field theory that describes the interaction between electrons, between positrons, and photons. For people who have taken quantum field theory classes, this is the Lagrangian. F mu nu describes the electric and magnetic field, and psi is an ordinary 4-component Dirac spinor field. When the electron mass is ignored, this Lagrangian has a symmetry. It's a U1 global symmetry. It's chiral in the sense that it rotates the right-handed electron and the left-handed electron in the opposite way. In equation, it acts on the Dirac spinor in the following way with important gamma phi matrix. If you check the Lagrangian, it's invariant under this symmetry transformation. So again, by all means, we should probably call it a symmetry. This already sounds a little bit similar to the first part of the story. It's a transformation that lists the classical Lagrangian. But we all know that for QED, this is not the end of the story. In 1969, Adler, Bell, and Jacquet showed that this classical U1 global symmetry of the QED Lagrangian turns out not to be an exact global symmetry of the quantum field theory when you quantize the theory. The fact that a classical global symmetry fails to be a global symmetry quantum mechanically is the famous phenomenon known as the Adler-Bell-Jacquet anomaly. The ABJ anomaly was discovered in the context of the neutral pion decay, and it successfully determined the coupling constant between the neutral pion to the photon field. And that was a beautiful story back in the 60s. But if you think about the story a little bit more, there's something very, very slightly counterintuitive. So usually in physics, we celebrate when we find a new global symmetry of the quantum system. We use that global symmetry to derive new selection rules, new constraints on correlation function. In the context of ABJ anomaly, it was exactly the opposite. ABJ anomaly told you that there is not a symmetry that you would have naively expected. Now, the word anomaly is heavily abused in theoretical physics, so I should really clarify what I meant by here. By ABJ anomaly, I mean the symmetry at the end of the day is broken by this quantum effect. And just to show that I'm not alone in thinking about ABJ anomaly this way, there was a birthday conference for Steve Adler back in 1999 at IAS. And the title of the conference was called Symmetry Found and Lost. So at the end of the day, the symmetry was lost. The chiral symmetry is not there in the quantum mechanical QED. So how come we can learn all this beautiful quantitative result from the absence of the symmetry in the context of QED and pion decay? And wouldn't it be nice if some of this result can be reinterpreted from the existence of a symmetry rather than the absence thereof? And just to sharpen this counterintuitive aspect of the story, if you ask someone, is chiral symmetry a symmetry of QED? We really get a variety of different answers. So when I grew up, I always thought the answer is just no. Right? ABJ told us that there's no symmetry at the end of the day. But if you think about it a little bit more, in electron-positron scattering amplitude, the helicity is still conserved. You will never get a violation of helicity violation, even though the chiral symmetry isn't there at the end of the day. So when I first learned helicity conservation in QED, I learned it from Paskin and Schroeder. This is chapter 5 of Paskin and Schroeder, where the upshot is that the amplitude vanishes unless the electron and positron have opposite helicity. And the way they derive it, as you can see here, is to move the gamma 5 matrix from one end of the trace to the other end of the trace, and you get a minus sign unless the helicity is conserved. But they didn't say any word about the chiral symmetry of the classical Lagrangian. And they didn't dare to, because they knew down the road in chapter 19.2, they're going to talk about the ABJ anomaly, where the symmetry is going to disappear. So how can there be a conservation law, but without an underlying symmetry? Another reason we know the symmetry is going to be a little bit funky is that when you scatter an electron off a very heavy monopole, this is the famous Kalin-Rubakov effect. In the Kalin-Rubakov effect, it is known that the helicity will be violated by the S wave of the electron. So the situation in QED is really subtle. There is some conservation for certain subclass of scattering amplitude. But if you look at the most general possible processes, there isn't such a conservation. So that motivated me and my former student, Icho, who is currently a postdoc at IAS, and my longtime collaborator, Hota Len, who is a postdoc at MIT, to write this paper a couple of years ago, where we proposed that the chiral symmetry in QED is actually not entirely broken by the ABJ anomaly. Rather, it's resurrected as an exact non-invertible global symmetry in QED. I'm not going to give you the detailed derivation of this non-invertible symmetry, but schematically it takes the following form. So for any integer n, there's a new conserved quantity that we constructed in this paper from 22. The details of this expression doesn't really matter, but I want to draw an analogy between this operator and the operator we talked about during part 1 of the talk, the Kramers-Wigner symmetry in the Ising model. The Kramers-Wigner symmetry in the Ising model takes the form of a blue operator multiplied by a red operator. In both the QED case and the Kramers-Wigner symmetry in Ising model, the blue part is invertible, but it's not conserved. In the QED case, the invertible part is this exponential operator. The details don't matter, but I hope it's intuitive that exponential has an inverse. This operator does not commute with the QED Hamiltonian. Nonetheless, it's invertible. The fact that this doesn't commute is the statement of ABJ anomaly. In both cases, there's a second piece of the conserved quantity, which is the red piece. The red piece is non-invertible, but it is conserved. In the QED case, it's this projection operator. In the Kramers-Wigner case, it's the projection operator. In the QED case, it's something much more subtle. It's this complicated path integral over this Lagrangian. The physics behind this red piece is that this describes the physics of fractional quantum Hall physics in one dimension lower. And this is the physics of anions. And this operator ends up has a huge kernel whenever there's a magnetic monopole. So at the level of the slogan, you can say that the fractional quantum Hall state can be used to cure the ABJ anomaly. of QED. This operator D is an exact global symmetry in QED, and that explains the helicity conservation in positron-electron scattering. On the other hand, because this red part is non-invertible in the presence of the monopole operator, it also explains why helicity conservation is broken in the Kalin-Rubakov process. In QCD, if you ignore the quark masses, there's a similar non-invertible symmetry, and that has to be matched by the low-energy pion Lagrangian. In this paper, we show that to match this non-invertible symmetry in QCD, you have to have a pi-0 coupling to F mu nu star with coefficient exactly given by the correct value. So to put it in a maximally offensive manner, you can say that the neutral pion decay in the real world because of this non-invertible global symmetry. So if you look at look back in history on the fate of chiral symmetry, before 69, everyone thought chiral symmetry was a global symmetry. It leaves the classical Lagrangian invariant. That seems to be good enough. In the seminal papers by Adler, Bell, and Jakiv, they showed that chiral symmetry is not a symmetry quantum mechanical. But in this more recent paper, a new perspective was given where chiral symmetry was resurrected as a non-invertible global symmetry. Now you could have asked, back in 69, is it possible that Adler and Bell and Jakiv, could they have figured out this non-invertible global symmetry in their original 69 papers? But that was actually impossible because the fractional quantum Hall state was only discovered in 82, 13 years after the ABJ. And in this work, we combine these two concepts together. So the title of this slide is a little twist of the title for Steve Adler's birthday conference, where we claim that at the end of the day, the symmetry was recovered again. So in this context, for the chiral symmetry in QED, this exact global symmetry gives an alternative derivation for some of the results that we already knew in QED and also in QCD. But is there something else we can learn from this new kind of symmetries? So in the remaining time, I'll talk about two applications of non-invertible symmetry in quantum field theory. The first one is in the context of scattering amplitudes, based on this recent paper from last year by Kopeti et al. So scattering amplitudes in interacting quantum field theory is generally difficult to compute exactly. It receives perturbative and non-perturbative corrections. In two space-time dimensions, however, if you study the scattering between solitons, it turns out that there are rare cases where you can exactly compute the scattering matrices. This was pioneered by Sasha Zamolodchikov and many collaborators in the 80s and in the 90s. A recent paper from last year found that some of these exact S matrices are actually not compatible with the underlying non-invertible global symmetries for the massive quantum field theory. They corrected the answer that were there in the literature and found a new answer that respects all the symmetry of the quantum field theory. Now you might be wondering, Sasha Zamolodchikov is really one of my heroes in physics. Did he just make some factor of 2 mistakes back in the 90s? So what's the origin of the mistake? It turns out that the mistake was not an algebraic mistake. It's something actually deeper than that. What turns out to be the case is that crossing symmetry is very subtle in the case you do soliton scattering. The origin of the mistake, so crossing symmetry is a fundamental property of scattering amplitudes that interprets antiparticle as a particle traveling backward in time. Surprisingly, crossing symmetry is modified for soliton scattering. The intuitive reason is because soliton interpolates from one vacuum of your quantum field theory to a different vacuum. And when you treat the antiparticle as a particle traveling back in time, you go from vacuum number 1 to 2 to vacuum number 2 to number 1. And that very subtly gives you a non-trivial factor in the crossing relation. That means that the S-channel scattering amplitude is not literally equal to the T-channel scattering amplitude. So in this very nice paper by Kopeti et al., they derive a modified crossing relation. And using the modified crossing relation, they found the correct scattering amplitudes that respect the non-invertible symmetries. So this is one instance where the new symmetry not only point out mistakes in the literature that has been there for 30 years, but also lead to new physical phenomena. Now, one fun anecdote about this paper is that around this time last year in March, there was a celebration conference for the scientific contribution of Sasha Zamolodchikov at the Simon Center for Geometry and Physics. The conference was from March 11 to March 15. And this paper came up exactly the night before this conference. And that was a Sunday night, and I was checking archive, and I saw this paper. I was really interested in it. I read it immediately when it came up on archive. But I know Shota very well, and we were postdocs together at IAS. So I immediately sent him an email asking, did you intentionally put out this paper to point out the mistake by Sasha the day before his celebration conference? But really, Shota is really the sweetest person I know in physics. He actually had no idea that there was going to be a conference for Sasha the day after. So it was just one of those uncanny coincidences. So this is the first application. There's another one that's in the context of axion physics. So axion is one of the most promising hypothetical candidates for dark matter. It's also a very popular solution for a puzzle in particle physics known as the strong CP problem. And many people, there's a whole industry of people trying to perform various experiments to detect this hypothetical particle known as axion. Now, one of the most promising channel for axion detection is through the axion photon decay process. And this process is actually not unrelated to the neutral pion decay into two gammas. And in fact, there's a similar non-invertible symmetry in the axion physics as well. So in this context, you will usually see this plot where the horizontal axis is the axion mass, and the vertical axis is the decay rate from a single axion to two photons. The various color regions are the regions of parameter space that can be covered by the various experimental group. On this plot, there's a distinguished line, this yellow diagonal line that's known as the QCD band. And one of the theory there is based on two papers by Dine, Fischler, Swinicki, and Dynitsky, known as the DFSZ model. It's a very simple classic axion model. It's a simple Lagrangian quantum field theory, and it's usually highlighted in the landscape of the axion model. But what's special about this model? There are millions of other axion models in the landscape of model building. And it was never really clear to me what's really distinguished about this line. Of course, it has some connection to do with the grand unified theory, but is there something fundamentally distinguished about the DFSZ? So in this papers I wrote with my former student Icho and my collaborator Hota and another student Matthew Forslam from Stony Brook. And also there was an independent paper by Matt Rees. We found that there's actually something physically distinguished about the DFSZ line. We gave 4 derivations of the statement I'm going to make in the paper. And one of them was using the generalized non-invertible symmetries in these axion models, where we found that under various mild assumptions, which I'll be happy to elaborate more after the talk, that any QCD axion model below this DFSZ line in this gray region must necessarily face the axion domain wall problem in a post-inflationary scenario. Okay, so I added a lot of words, a lot of adjectives in this sentence, and it might not make any sense for people not working in this field. So if I translate it in plain English, it just means that life is harder in the gray region. It's not impossible, but you just have to do more work if one day we find an axion model in this gray region. Anyways, this simple reasoning actually gives an invariant distinctive role of the DFSZ model in the wide landscape of axion model. All right, so there are many, many other applications of generalized symmetries that I won't be able to cover here. ranging from quantum field theory, gravity, condensed matter physics, a little bit of quantum information in the recent years, and also particle physics. Let me shamelessly advertise my talk tomorrow. I'm giving a talk at 11 tomorrow at the high energy group, where we were guided by a certain non-invertible symmetries in the context of lattice fermion. Using the non-invertible symmetry there, we find a new lattice chiral symmetry in the simplest possible staggered fermion model. So for any of you who are interested, please come to my talk tomorrow. So here's a quick summary. The upshot of the talk is that symmetry need not be invertible. What's done cannot be undone. The simplest example is the Cramer's Wigner transformation of the Ising lattice model. Turns out to be a non-invertible symmetry and imposes non-perturbative constraints on the phase diagram. And a closely related example is the chiral symmetry in QED and QCD, where the chiral symmetry is shown to be resurrected as a non-invertible symmetry. And this is one reason I really like about this research program. The Ising lattice model in 1+1D is a very, very different model compared to the 3+1D QED. The Ising lattice model for finite number of qubits is a finite dimensional system. It's in 1+1 dimension. It describes magnetization. QED, on the other hand, is in 3+1 dimension. It's a continuum quantum field theory. It explains the reason why we can see each other in this room. Even though they look so different, if you look at their detailed symmetry structure, they actually have very similar patterns. And this is one instance where thinking about the underlying symmetry really unified different physical models and phenomena into one framework. And there has been a lot of activities in this research program with various Simons collaborations, with various overlapping Simons collaborations. For people who are interested in learning more, there are various lectures in the past few years where the recordings are available online. And starting from next Monday, there's going to be a KITP program running from March to May on generalized global symmetries in QFT. And we're very proud of the logo we come up here that shows that this is really an interdisciplinary endeavor trying to bridge different communities together. All right, so this is my final slide. I guess I'm a little bit early on time, but I guess no one in the history of physics would complain about a talk ending too early. But this is my final slide. So you guys are great. You've been so patient, listening to almost an hour of spiel of how great symmetries are. But you might think, why do I care about all this, right? Someone hand me a problem, a physics problem, and ask me to solve it. You can just shut up and calculate. Do the calculation, you get to the bottom of it, you get the answer, you celebrate, and you call it a day. And in fact, for physicists with a lot of muscles, like many of you are, that's kind of the approach we usually take. If you find a solution, you don't need a symmetry. On the other hand, if you are a skinny physicist like myself, we try to use every little tricks we have available in our pockets. And that's the way I view symmetries. For instance, if someone hands you the Schrödinger equation for the hydrogen atom, you can solve it in Cartesian coordinates. You can solve it in X, Y, and Z. There's nothing wrong with that. But for me, I would prefer to solve it in the spherical coordinate, making use of the SO3 rotation symmetry. There's one example of this. And I think more often than not, the symmetry was the first clue that hint to a more complete and exact solution of the underlying system. And my favorite example is, again, the Ising model in 1+1D. So let's go back to this paper by Cramer and Wigner. Let me remind you, this paper was written in 1941, 3 years before the seminal paper by Lars Onsager, where he solved the Ising model exactly. In Cramer and Wigner's paper, they didn't have the exact solution for the Ising model, but just using the non-invertible symmetry in the modern language, they can determine uniquely where the transition has to happen. And this work influenced Onsager in leading him to finding the exact solution for the Ising model. You can read into the original paper where he said that even though his solution to the Ising model It's completely self-contained. You don't need to know Kramers-Wigner paper, but Kramers-Wigner's paper was the motivation that encourages him to find a final solution. In the past few years, we have seen developments similar in spirit to the story here, of course, are far less in importance and significance. But in the years to come, I hope there will be more examples like that. And with that, thank you for your attention.
Thank you very much for the beautiful talk. Any questions? Okay, say.
When you wrote this chiral symmetry, you added terms that is similar to quantum Hall. It's on a 3D manifold, right?
Yes.
It's like the symmetry is generated by moving quantum Hall systems, those floating, right?
That's right. So the operator I wrote over there. So it's an operator, right? So by definition, an operator is something that you insert at a fixed time and it acts on the Hilbert space. It spans over the entire space and it acts on your Hilbert space. So here, the 3D manifold you are referring to is the entire space. So this is the Euclidean Lagrangian for the fractional quantum Hall physics. But it's important to stress that this is an operator at a fixed time. And therefore, I didn't change my Hilbert space for QED. The Hilbert space this operator is acting on is still the good old-fashioned Hilbert space of QED. That's made out of photons, electrons, and positrons, etc. So this is a new operator acting on the old Hilbert space.
But I guess another interpretation is that you have a two-dimensional system that moves in time, and you can have a quantum Hall system on a 2D space, and that quantum Hall system moves through 3D, and it sweeps this three-dimensional slice. Is it a good interpretation?
So here I interpret it as an operator, but alternatively, the entire expression is Lorentz covariant. So I can alternatively make it extending time, but localize in one direction in space. And that will become a defect of this QED. So that will be closer to what you described. And it's an interesting question. So this is a defect that modifies the QED Hilbert space. And it will be interesting to understand what kind of states live there.
But in that case, you have to add degrees of freedom on the defect.
But that's always the case for defects. But when we study Kondo problems, you add impurity at one site. When you view it as an operator, then it acts on the same Hilbert space. When you make it a defect, that generically will include new degrees of freedom. And in this case, the new degrees of freedom will be some anyons.
Okay, John?
Yeah.
So Wigner defines symmetry differently than you do. So he drew a different conclusion,
Yes.
but he was very good at thinking about things in general terms. Should he have suspected that he was missing something, defining symmetry the way he did?
Right. So the thing he assumed in his theorem is that he wants the operator to preserve probability. And that's a totally reasonable assumption to make, especially in quantum mechanics. Here, the reason that non-invertible symmetries become more pronounced when you go to many-body quantum system and quantum field theory is that the moment you depart from quantum mechanics to system in 1+1D and higher space-time dimensions, the notion of localities becomes important. And that's one thing I didn't get to emphasize throughout the entire talk, that all the symmetries I talk about today, they in some sense satisfy a very strong notion of locality. And that's something that's not there in Wigner's reason. So Wigner assumed something more, but he also didn't address locality because he was mostly focusing on quantum mechanics.
Many examples you mentioned today involved projection operator.
That's right.
Is it always the case or?
Very good. So indeed, in both examples I mentioned today, the symmetry operator takes the form of a unitary operator times the projection.
Mhm.
In the QED case, it might not be super clear.
Well, but it
why
doesn't
this-
act on, so, yeah, okay.
It doesn't look, this complicated thing actually
Yeah.
serves as it acts as a projection.
Right,
With respect to the magnetic monopole
Yes.
flux. Now, to your question, the short answer is no. Not every non-invertible symmetry.
so there are
take-
counterexamples.
Exactly. One very famous counterexample was actually in Alexis' paper from 20 years ago. Yeah, this is the golden chain model. This is a Hamiltonian lattice model defined not on a qubit spin chain, but on a more general Hilbert space. In that model, there's an interesting non-invertible symmetry, which they call topological symmetry, that does not take the form of a projection times a unitary operator.
But you still have, but I'm confused. So it doesn't have corners?
It doesn't have
Does
what?
it have corners?
Good, that's an excellent question.
If
As
it
an
doesn't have corner, why it's not invertible?
Very good, very good. So that's the thing I didn't get to mention today. That's the importance of locality. So as an operator, it does not have a kernel. So you can find the inverse operator of the topological symmetry that Alexei talked about 20 years ago. But the inverse violates locality. It doesn't map local operator to local operator in a nice way. So in that sense, it's non-invertible.
Okay, well, it's invertible, but in local sense.
It's invertible as an operator,
Mm.
but it's non-invertible if you view it as a more general object.
Okay. Any other question? Lucy, you had a question? Or- No,
I have another.
oh, you have another question, okay. Oh, we have time, yes.
There are other field theories where global symmetries have anomalies,
Great,
as opposed to
Great.
gauge anomalies, which are something different.
great.
Are they always non-invertible?
Excellent question. Yeah, so let me answer that. So when I talk about holistic conservation, I mentioned that in chapter 19.2 of Peskin and Shorter, they talk about the ABJ anomaly of 3 + 1 DQED. But I wonder, does anyone remember what chapter 19.1 was about? Well, 19.2 is about 3 + 1 DQED. It's only natural that in 19.1, they talk about QED in 1 + 1. So what's the oldest anomaly in the human history? Well, that's the Schringer anomaly. Schringer in 1959 noticed that the chiral symmetry in 1 + 1 DQED with massless electron is anomalous. That can be diagnosed by the Schringer term in the commutation relation. So now coming back to John's question, okay, that's another example where there's an anomalous symmetry. Does that become a non-invertible symmetry? The answer is no. So the short answer to your question is no. It depends very much on the details of the kind of anomaly the original symmetry is suffering from. There is an organizing principle in how to understand all this, but I purposely not mentioning that because that will require more data. But I'll be happy to talk about that more.
But Schwinger's anomaly also led to definite predictions, like the mass of the meson could be inferred from it, but I can't think of that as being.
That's an excellent question, yeah. But I feel like that has more to do with the fact that the model can be bosonized into a free scalar, and then you just solve it. I don't know if there's a symmetry explanation for that. I should also comment that in the Quermers-Wigner case, you could have asked, where's the anomaly there? What's the analog of the ABJ anomaly in the context of the Quermers-Wigner symmetry in the Ising model? And there is actually an anomaly that has to do with the Kitaev chain. But I didn't present the story in that way. That's one of the 5 derivations that I skipped in the first part of the story. So both cases I talk about in the talk today comes from an anomaly, but more generally, not every anomalous symmetry becomes non-invertible. That's the short answer to your question.
Okay. Any other question? Is everything clear? Okay, thank you very much.